When I say work, I'm sure the first thing that comes to your mind is picking up a box or grabbing a book and actually doing some work. Well, let's explore what the physics definition of work is. So, let's get down to work. Don't forget to pause and take a few notes where you may need to. We're starting off with the basics of what work is. Work is a form of energy. The unit of measurement for this is joules. Work is a scalar quantity, which means it has magnitude only. For work to be done on an object, we have to consider three factors. The first is the force. The second is the angle formed between the force and the displacement. The third is the distance that the object travels. This now brings us to the work equation. The work equation is represented with a formula which stands for W is equal to F times delta x times cos theta. Now let's look at each part. W stands for the work done, and the unit of measurement for this is in joules. F stands for the force, and the unit of measurement for this is in newtons. Delta x stands for displacement, and the unit of this is in meters. And finally, angle theta. This stands for the angle between the force and the displacement. So if we're looking at a practical example, if we exert a force on the sofa, it travels a distance. It only travels this distance because a force is applied to it. And by doing this, we say that work is done. So these are the variables used in the work equation. Now, let's unpack each part of the work equation so we know exactly how we can use it. Let's begin with the forces. The first question to ask is, what forces do we use when we are using the work equation? The first force we can look at here is the applied force. This is the force that is exerted onto an object. The second is the normal force. This is the force exerted by a surface onto an object. The third is the frictional force. This is the force that opposes the motion. The fourth is the force of gravity. This is the force exerted by gravity onto an object. And the last one is the tension force. This is the force that a rope, a string, or a spring exerts. The next variable we are looking at is displacement. We can ask the question here, what is displacement? Displacement is represented with the symbol delta x. Delta x basically means there is a change in displacement. So displacement is the distance an object travels from the start to the end of the motion. Look at this example here. We have a car placed at the start position. It then travels to the end position. The distance between the start and the end is what we refer to as the displacement of an object. And now for the next variable. This is the angle. So what angle do we actually look for? The angle is found between the force and the displacement. The best way we can actually understand this is by using an example. So in this example, we take an object, we place it at the start position. We then exert a force onto this object. And when we exert this force, it's going to cause the object to move. The object will move from the start position to the end position. And as you can see, once again, between the start position and the end position is where we would find our displacement. I want you to now focus on the directions. The displacement of this object is to the right, and the force that is applied to the box is also to the right. So can we see that both of them go in the same direction? The force is to the right, the displacement is to the right, and we say that when this happens, there is no angle being created. Therefore, the angle that is between the force applied and the displacement is actually equal to 0. Let's now put what we've learned into use. Before we actually solve for the angle theta, I want you to always keep this in mind. The angle is found between the force and the displacement of the object. So in this example here, we have a person pushing the box to the right. From this, we can draw a free body diagram, which you have learned in grade 11. In our free body diagram, as we can see on the right, we have the normal force acting straight up, the force of weight acting straight down. We then have a push force or an applied force to the right, and then the force of friction acts to the left. You can now use the free body diagram when you are solving for the angle theta. Always keep in mind that the displacement acts to the right. So let's go look at the first force, which is the applied force. The applied force, according to the free body diagram, acts to the right, and remember our displacement is also to the right. And there is no angle being created here. So the angle that we say we are using is angle 0. Next one is the normal force. According to our free body diagram, normal force acts straight up and the displacement acts to the right. And the angle being created between these two forces is angle of 90 degrees. Next is the frictional force. Frictional force always opposes motion. So frictional force acts to the left, displacement acts to the right. They are both in a straight line. So we find that the angle being created here is 180 degrees. And the last force to look at is the force of gravity. Gravity acts straight down and the displacement acts to the right. And the angle being created between these two is angle 90 degrees. Okay, that was a lot of information. I think we can pause for a while and take a break. While you're on your break, go and grab your calculators because we're going to be using it for the next example. And now for our example. In this example here, it says a person pushes a 2 kilogram block with a force of 100 newtons to the right over a distance of 4 meters. The box experiences a constant frictional force of 7 newtons during the entire motion. Calculate the work done by each force. So just like how we had the previous example, we're going to use a similar format to actually answer these questions. Now we're just putting numbers to this equation. So looking at the first force, which is the applied force, write down a list of information that you have been given. You have been given that the applied force is 100 newtons, that the delta x is 4 meters, and we know from the previous example that the angle that's created here is angle of 0 degrees. Once again, the applied force goes to the right, displacement goes to the right. That's the reason why our angle theta is 0 degrees. Now let's substitute this into the formula. The formula we're using is the work equation, which is W applied is equal to F applied times delta x times cos theta. The F applied is 100, the delta x is 4, and the cos of theta is cos 0. Put all of this into your calculator and we find that the work done by the applied force is actually 400 joules. And now let's find the work done by the other forces. The next force we're looking at is the normal force. Remember that the angle created here is angle of 90 degrees. So cos of 90 is actually equal to 0. So even though we're putting this into the equation, we find that the work done by the normal is actually 0 joules. And now for our frictional force. Here we find our substitutions as follows. The force of friction value is 7 newtons, the delta x is 4 meters, and the angle that's created here is angle of 180 degrees. So putting all of this into the equation, we find that the work done by frictional force is actually a negative value, it's negative 28 joules. And the last force we're looking at is the work done by the force of gravity. Here again, the angle created between the force of gravity and the displacement is angle of 90 degrees. So cos of 90 is equal to 0. So the work done by the gravitational force is actually equal to 0 joules. This brings us to the end of our lesson. I hope you've learned something. Here's an example that you can try out. Don't forget to leave your answers in the comments below.